Okay, so it looks like we're recording. Off we go. Let's see. Oh, and I hadn't pulled up my... Okay, oh my gosh. Let me pull up the notes. Sorry for the delay here. I forgot to do it. Let's see here. Lecture notes. Chapters. Okay, so here's where we were last time. Well, here's what we were talking about last time. This idea of... what do you do if our domain is dimensionally weird? And this is the first example we're considering, right? So the idea of a one-dimensional curve, but in a two-dimensional world, and it doesn't fit any of our previous structures. So we come up with a new construction. I mean, this is morally the same as every other integral we've ever done. We take our domain, whatever it is, however weird it looks, we chop it up into little pieces on which the question that we're interested in is easy. And then we add it up. That same basic idea, right? Just adapted to this different geometry. And name and a notation, of course. Then we also adapted an old strategy for how to actually compute this. Big idea. Again, I'm just hitting the broad strokes because we talked about the details last time. But when you have an undesirable domain, the big strategy is find a way to view it as an image. And in this case, our undesirable domain being a curve, we know how to do that. Parametrizing, literally, views that as being an image. Right? And then again, detail, stretching factor, yada, yada. And so we have now a computationally convenient formula for how to compute these, new kinds of Riemann sums that we just created. And then we did several examples. Okay, so we're going to pick up now where we left off with another example. Well, another attempt at an example. And something's going to go a little bit wrong with this example, just to give you a heads up. So anyway, here we go. Honest intentions. Y'all remember this formula right here. Work is force dot displacement. Keep in mind, force is a vector, displacement is a vector. Right? And the old high school formula that treats them as scalars is, that's the situation they're in. They can't assume that you know what a vector is, and so they tell you this little oversimplified version. Well, here's the thing. This is actually a little oversimplified too, right? This does recognize that the force is a vector and displacement is a vector, but it also kind of assumes implicitly that the force is constant over the entire displacement. And that's not how the real world works necessarily. Right? Sometimes forces are more later in the process and less earlier in the process. It also kind of assumes that your displacement is over a straight line path. Again, not all paths in the real world are straight lines. So, how do we deal with a situation like this where we're moving over a path that looks like that? Not a straight line path. We are currently unarmed for addressing such a matter, right? And then what if the force that we have to exert along the way is, as you'll notice here, highly non-constant? Well, again, we don't have any way to deal with that at the moment. Right? So the big idea then is, again, it's a ripoff of every other integral we've ever done. We're going to take our path here. We're going to chop it up into little pieces, such as, for example, this little piece right here. Right? And we focus our attention on that one little teeny tiny little piece, which is approximately straight. Not exactly, but pretty close. And round off error is going to go away in the limit, but it's plausibly borderline kind of straight. And it covers such a small amount of ground, right? All the points on this little piece are really close to each other, again, in the limit, as we chop finer and finer. And so over such little pieces, as long as our vector field is continuous, which we are assuming in, a course like this, the force, we can conclude, would be approximately constant. Again, not exactly, but the round-off errors are going to go away. So just like other, kinds of problems that we've addressed, this idea of chop it up, add it up, turns a problem that we don't know how to solve into a whole bunch of little bitty problems that we basically do know how to solve. and then we add up over the whole. And it seems like we're nicely situated to call this just another, I mean, at this stage of the process, feels like this is going to turn into another scalar liner. Now, before I get into details, I do want to acknowledge one little worry, one little uh-oh that we can already see, and that is this question already has something about it that we didn't have to worry about when we were computing, mass or moment of inertia or stuff like that. And that is the direction that we do it matters here. Right? If I'm, for example, let's suppose this is a mountain road that I'm driving along. Well, it matters very much that I'm going that direction as opposed to the opposite direction. Right? Driving up the road to the top of Pikes Peak takes a lot more energy than coasting down that same road. Right? Does everybody buy that? And in fact, I would say there's a stronger true statement, which is when you're driving downward, if you're in one of these cool new hybrid type cars that's all about the battery, you can actually recharge your battery by driving downhill. Right? You just put on the brake. Right? The brake is not friction brake. Actually, don't quote me on anything I'm saying about specific automobiles. The details I don't know. But to some extent, when you put on the brake, you get what's called electronic braking, right? And there's a complicated arrangement of coils and magnets, which all of y'all engineers will totally learn about at some point, right? And the motion of the wheels creates a motion of magnets, which does some cool stuff with Maxwell's laws, and actually creates a current in the coil. And that current will literally recharge your battery. So in fact, not only do you not expend a positive amount of work, you actually regain energy. In other words, you expend negative work. Right? So which direction you go matters dramatically. And that's not the case in any of our prior examples. And I think this is worth raising the eyebrow, right? I mean, let's just for convenience, let's look at this example right here. We're worried about painting the fence. How much paint is it going to take to paint the fence? Will it take more if I paint it clockwise instead of counterclockwise? No. It's the exact same amount of paint. Will it take me negative paint? Will I gain paint if I paint in the opposite direction? Nonsense. Silly, right? Ridiculous. We've never seen anything like this issue before now. And so that's an eyebrow raiser. That should make you think, uh-oh, something about this is fundamentally different. And just keep that thought in the back of your mind as we proceed. Okay. So, by the way, we address this with the following term. We don't call this a curve. We're going to call this an oriented curve. And the idea is that this word oriented is a reference to what we call an orientation, the orientation being an indication of which direction along the curve we are going. Of the two possibilities, are we going that way or are we going that way? Okay. All right, so moving along. On each little piece of curve, and I've just got a sort of a blown up image of that little piece of curve right there, and here you go, there's our little piece of curve. And the whole point to breaking it up was that on each little piece of the curve, we have basically a pretty simple question. We can estimate our displacement by the dx vector. That's, velocity times dt, and of course it doesn't account for the little teeny tiny, little bitty bit of curvature there, but in the limit that's going to not be a problem. And then there is the force that's being exerted, that we are exerting over that little piece of curve, and that's an approximately constant force over an approximately straight line, and force dot displacement tells me how much work it takes to move along that little piece of curve. And then you add them up. Right? This formula for work You add up over the entire curve, whatever the entire curve is, and you've got yourself an answer to the question of how we're going to compute that total amount of work. How does that feel? Is that everybody okay with that? Everybody see how we're doing the same sort of chop it up, add it up approach that we did previously for fence painting and mass weighing and stuff like that. But we get a very different looking result. And y'all will recall when we first started talking about line integrals, I gave this mysterious distinction. I talked about it. Well, it's a scalar line integral because, believe it or not, there's another kind of line integral coming, and here it is. This is what we call a vector line integral because, check it out, the differential is a vector. Creepy and weird, but here we are, right? And furthermore, the integrand right there, vector. And by the way, in the same spirit, look at the multiplication here. This is not a multiplication of scalars. This is a vector multiplication. So arguably reason number 3, that reasonable to call this a vector line integral. Okay. All right, now again, just like when we first wrote down scalar line integrals, there is this looming question of, okay, that's all well and good in the abstract, but what on earth am I supposed to do to actually compute this thing, right? So yes, we do need to address that, but just a point of order, I think it's always critical to make sure we are clear on what we are computing, right, before we get our nose down into the ground and worry about the actual computation. So don't lose track of what it is that we're computing. When we write down something like this, we have a vector field, we have a curve that we break up into pieces with corresponding displacements, and for whatever reason, in this case because of work, right? But in general, for whatever reason, we want to dock and add. All right, so computation, how's that work? Good news, we're actually already fairly well set for this. Let's see if I can get this all on the screen at the same time. How do we compute this thing? I'm going to remind you from Chapter 3, stuff we already know from Chapter 3. You can flash back in your notes. This would be section 3.2, I think. Pretty sure it's 3.2. Anyway, early Chapter 3. And, we talked about that's where we introduced this idea of the dx vector. And then at the same time, we introduced this idea of the unit tangent vector, capital T, and how both of these relate to the velocity vector, x prime. Right? So all of that is old news. Everything in green there, old news. And in particular, back in Chapter 3, we connected these various objects by way of these 3 equivalences, right? So all 3 of these things are just the same thing. dx is x prime dt, which is TDS. And I remind you, if you may have forgotten why these equations work, just go back in the notes or in the videos, right, to the Chapter 3 stuff, and all the explanations are there. So, beautiful idea. Check it out. dx. This dx right there is one of these 3 things that I have now different versions of. And so all we're going to do is just plug those in, and very conveniently then we now have 2 more, colors, hang on, 2 more perfectly reasonable ways to write what is in fact exactly that same vector line integral that we already motivated. All right, y'all right? Is that good? Why are these useful? Let's talk about these one at a time. Let's talk first about this one. Why would I like this version of the expression? And what's nice about this is that we've already done the pullback. This is already an integral on the t-axis. This is single variable integral, right? X prime that's going to be written in terms of t. And f is a function of position, which is a function of t. Right? So everything in here is already pulled back. This is primed for plug and chug and go ahead, fundamental theorem of calculus and all that. Right? So from a plug and chug computational standpoint, this is the thing. All right. This one there are some nice things about this notation, but I actually kind of dislike this notation. Let me just try to explain why. I've already put in a bunch of words about how vector line integrals are fundamentally different from scalar line integrals. And this notation here kind of makes it look like this fundamentally different thing. Look at that, it's a ds at the end. It looks like a scalar line integral. My own personal feeling, there are different points of view on this. My own personal feeling is that when things are fundamentally different, we shouldn't try to make them look like each other. We shouldn't try to conceal that difference, right? We need to understand that difference, and I find it very helpful myself when the differences manifest in the notation, right? I like this notation over here because it looks different from a scalar line integral, which is good because it is different from a scalar line integral, and let's be upfront and forthcoming about that. That's my position on that. Anyway, all three of these notations are fine. By the way, this notation has another really nice thing about it, and that is it's very transparent. Why are we computing this in the first place? Well, it's because there was a vector field representing the force. There it is. And we're moving over little pieces of the curve over which I have little displacement vectors dx. There it is. This is just straightforward, completely forthcoming about why we're interested in this in the first place. In some sense, this is the simplest of our notational choices, yeah.
Is the right-based integral, is that like converting from the vector line integral to scalar line integral?
It's still a vector line integral. It's just kind of trying to conceal the difference and kind of make it look like it's a scalar line integral. But it's still a vector line integral because, equals means is, right? It literally is a vector line integral. It's just kind of sweeping the distinction under the rug, which to me, again, is why would we ever want to sweep important distinctions under the rug? I don't get it.
So you're just doing it in terms of the line, even though it's vector.
Yeah, that's right. I mean, this TDS is literally dx. Yeah. Okay. All right, so let's do an example, and then we'll have much more to say, of course, but it's always good to get one under our belts. Reminder, work is the vector line integral, and vector line integrals are computed by way of this formula, which depend, you see right there, depend very critically on our parameterization. So we're going to be doing all of that in this following example. Here we go. We have a force, and we want to compute a work as we move along a certain curve. This question is tailor-made, right, for the formula that we just wrote down. There is a little subtlety here, and I don't want to get distracted in physics, right, because this isn't a physics class, but there's the awkward little reality that we have to distinguish between two different forces. Let's look at this red pen that I have in my hand right here. There are actually two forces acting on this red pen right now. Gravity is pulling down. I am pushing up. The fact that I am pushing up is why the pen is not accelerating down due to the gravity, right? So there are two forces in play, one up, one down, and they are exact negatives of each other, right? So when you're solving a problem like this and a force is given to you, you have to ask yourself a very reasonable question. Well, wait a minute. Was I given the force that I'm interested in, or was I given the negative of the force that I'm interested in? There are two forces. Right? So you got to think it through, and there is no shortcut around comprehension here based on language or something like that. You've just got to digest what has been expressed, right? and think about, wait a second, is that the force that I want, or is that not the force that I want? So it says right here, wind is exerting the force on you. I'm trying to figure out how much work do I have to exert, or I guess we should say, let me keep it straight. We want to know how much work you are going to have to exert. If we want to know how much work you exert, we need to know the force that you exert. The wind exerting a force on you is the opposite of what you exert back on the wind. Does that make sense to everybody? So because of this oppositeness, right, and just it happens to be the way the givens in this question were given, that we have a minus sign here to figure out the amount of force that you push with, right? And it's the opposite of what we were given, namely what the wind exerts on you. Does that make sense? I hope that's okay. And again, this is a point of physics. And if you have any questions about this, come to office hours. I'll be happy to discuss and give examples and clarify. But that's why that minus sign is there. Other than that, notice we just have vector line integral, right? Vector field dot displacement added up over the entire curve. Per the above formula, step one is we're going to have to parameterize. How do we parameterize that curve? Okay, well, flashbacks to chapter 1. And by the way, this would be a good time to go back into chapter 1 and remind yourself of all those various little tips and tricks, right? Remember I gave you a toolbox full of tools for how to parameterize stuff. There's the graph parameterization, and there's various other, little cool tricks that work here and there. So in this case, conveniently, we're going along the top half of the unit circle, which is easy to parameterize. All right. By the way, I'm just in my own self-defense, I'm going to note that I'm deliberately going to sweep a certain point under the rug just for the moment, and for dramatic purposes, I'm going to bring it up later. So just for the record, I know the mistake I'm making. But anyway, so there's a parameterization, and these are the values of t, by the way, that correspond specifically to the top half of the unit circle. So there's that. Here's how you take a derivative. Y'all remember how to take a derivative of a parametric curve, right? One coordinate at a time. And now plug and chug. It's all over but the crunching. There's the formula for how to do a pullback, right? This is one of the formulas that we just wrote down. dx is, after all, x prime dt. And I've computed x prime. There it is. That's x prime. Let's see, the force that I was given, this F, right? I was given that right there. Now, yes, I need the negative, but I've already inserted the negative, right? This explicit minus sign that I've written right here accounts for the fact that the F that I was given is the opposite of what I actually need, right? So that having been accounted for, don't put another minus sign in there. That's a double negative. That's not good, right? The bounds. T goes from 0 to pi, so T from 0 to pi, right? We're just plugging into the formula. And now I might just have to finish one last little detail of the pullback, and that is how do I rewrite x and y, right? What am I going to do about this y right here, for example? And let me remind you, and this is again one of these points that very often students tend to kind of forget about, but the variables themselves that you need to pull back through the parameterization, the formulas for them are literally straight up full on given in the parameterization, right? So what is y? Well, y is sine t. And so you'll notice that's how I plug that in right there. Everybody happy? And you multiply some stuff out. You simplify conveniently, Pythagorean identity kicks in, and this turns out to be a nice and easy integral. Okay. So the good news, computing a vector line integral directly from the parameterization is a pretty straightforward process, and actually there's something about it that's even nicer than scalar line integrals, and I think this is fun to point out. You may recall with scalar line integrals, we had to compute a stretching factor. That stretching factor was the magnitude of the velocity. In other words, it was the speed. How do you compute magnitudes? Well, with a square root, right? Bummer. Square root in your integrand. Nobody wants that. How come we didn't have to do that here? Well, we kind of did in a little bit of a way, and I just want to point out where it is. Again, here's our three formulas. Let me expand. Another way to write this is f dot t magnitude of x prime dt. Now that's a weird way to want to write it. What I like about this is that it allows me to emphasize how I wanted the pen, sorry. It allows me to emphasize how this just manifests differently in these two different integrals. Specifically, and by the way, there's your stretching, sorry, highlighter mode. There's your stretching factor. Right? And just notice that in the version on the left, the stretching factor is hidden inside of x prime. And in the version on the right, the stretching factor is hidden inside of ds. So the stretching factor is in there. It's just you don't have to compute it explicitly. We can get the effect of the size stretching factor that we need simply by the fact that we've written x prime here that has that stretching factor built into it. Okay. Alrighty. Let's see here. Let me get back to where we were. Okay. That example being done. Let's worry about the parameterization again. Y'all may recall I had this kind of little point of formality that had to get mentioned when you're talking about computing something with a parameterization. You just choose the parameterization. Does it matter which parameterization I choose? What if he does one parameterization and I use a different one? Are we going to get different answers because we use different parameterizations? And the punchline was that no, it doesn't matter at all. You'll always get the same answer no matter the parameterization. Tempting to say the same thing would be true here. And it isn't. Not quite. Important subtlety. Easy to mess up. Remember, we already talked about the fact that we're doing an integral on an oriented curve, right? So the direction we're going matters. The fact that I'm going that way, specifically, is part of the scenario we're entertaining, right? We're going in a specific direction along a curve. We're not just adding up, inert dumb scalars along a curve, right? So when you ask the question of, hey, does the orientation matter? Don't lose sight of the fact that, the direction you're going is part of the deal. So when you parameterize, you'd better parameterize the right direction. If you parameterize the wrong direction, you're not answering the same question. Does that make sense? You don't want to accidentally compute the amount of work it takes to go down the road of Pikes Peak when what you cared about was how much work does it take to go up the road of Pikes Peak. So that's a big deal, of course, and not surprisingly, it's a pretty simple punchline. If you go in the wrong direction, every single one of your dx's is just going to be backwards. That instead of this, you'll have a negative sign in every single term in your summation, and that's bad, but it's also conveniently simplified as, your total will also be off by just a minus sign. So anyway, that does matter. You do have to be careful about it. The orientation makes a difference. just to formalize that, this is just mostly a notation and a theorem to say what we just said casually. The idea here, and this is the book's notation, I think it's perfectly reasonable, that little superscript of a minus is notation saying, I want to talk about the same curve as C, but oriented the opposite way. That little superscript means turn around and go the other way. Is that cool? And then the punchline of the theorem is that if you do go the opposite direction, the value you get will be wrong by a factor of -1. Does everybody see how this, again, this is just writing down in kind of a more explicit way what we already kind of talked through. Okay. All right. And let me put a more positive twist on this. Just a more, glass half full take on what this theorem says. If you need to compute a line integral that's oriented in an awkward way, right? Let's suppose that that's, for whatever reason, going to be, it's going to be hard to parameterize in the backwards direction, or something else about it going that way is inconvenient. Hey, no sweat. You can compute that by orienting the more convenient direction. In other words, feel free to just flip the orientation at the low cost of just having to insert a minus sign on your answer. Right? So this is both a documentation of how you can mess up and also instructions on how to change a harder problem into an easier problem. And that's a really nice point of view when you're actually plugging and chugging. So let me show you an example of all this in action. First, let me show you how to do it the old-fashioned way. We're going to look at the previous example. This time, though, walking the other direction, clockwise instead of counterclockwise. Now let me go back up here and do the mea culpa. I completely ignored the direction when I solved this problem, right? I looked at the top half of the unit circle. I parameterized the top half of the unit circle. I didn't give any consideration to whether this parameterization is going the way we're supposed to or not the way we're supposed to. I completely ignored, in other words, that it says right here I need to be going counterclockwise. Completely ignored it. And that's wildly inappropriate. Now, again, for dramatic purposes is why I sort of, pocketed this point and to bring it up now. But y'all can't do that on the exam, right? You've got to get this right. You've got to parameterize, or at least recognize the need for parameterizing in the correct direction. Now, I got lucky. This happens to be going in the correct direction. And in fact, it's not hard to see why. There's a couple of ways you can see why. If I were to look at the top half of the unit circle like this, I can just think about how does this parameterization work. You can just kind of geometrically, okay, what happens when t equals 0? Well, I'm here when t equals 0, and as t increases, I just move along the curve, and I'm clearly going counterclockwise, as I'm supposed to. Or, alternatively, if you prefer, you can look at the velocity vector that we computed. You had to compute anyway. Okay. And then just look at how that velocity vector shows up on the curve, and pick any point on the curve you like. Whatever, doesn't matter. I guess we'll take the starting point. Let's plug in t equals 0, which puts me here. And when t equals 0 puts me there, my velocity, plug in the numbers and all, is straight up. And there you can see, as desired, we are going counterclockwise. All right, so I kind of, again, completely ignored this very important point in my first presentation of this example. This is really what you need to do. Okay, so looking back now at our new example, we're going to do the same thing, but we want to go clockwise now instead of counterclockwise. Well, how are we going to deal with that? I'm going to give you 4 different answers to this question, just to show you your options. Again, tools in the toolbox. 2 of them are going to be direct. I'm literally going to parameterize counterclockwise. Clockwise, like it says. I'm going to parameterize clockwise with kind of 2 different approaches. And then we're going to plug and chug the old-fashioned way. And then I'll show you 2 other takes, in my opinion, on them. But let's do these first. If you're going to recognize that you're going clockwise, I like the idea that you can recognize that by giving an indication on your diagram of what t actually is. Right? If you are indeed going clockwise, then at t equals 0, you're on the point on the left. This is where you start. Clockwise means t equals 0 is going to be there. And as time passes and as I go clockwise, that means t will be increasing in this direction. So that is my angle t, which means this is my angle theta in the polar coordinates sense of the word, in the sense that allows me to convert, right, from an angle to rectangular coordinates. This is the angle about which I have formulas for x and y in terms of r and theta, and so that being my theta gives me that. So my x comma y is that. And yet another instance where we need to make sure we know our angle addition formulas. You can plug into the angle addition formulas, or if you remember all of your symmetries of the trig functions. I know it was a long time ago, right? But it's prerequisite material just never goes away. Take your pick, but anyway, that simplifies then to this. And then you can plug and chug by the usual means, and I encourage you to go ahead and go through that. Minus pi is the answer. Now here's a different take, another one that I like, another tool for your toolbox. This is what I need to do. I need to walk clockwise. Let's recognize that we already remember how to go counterclockwise. Counterclockwise is easy. Counterclockwise is our old friend. So what I have and what I want, you can see right here in the picture, very conveniently are reflections of each other. And you can just think about, well, how do you reflect over the line that is the y-axis? And the way that you do that reflection is that it manifests in this minus sign right there, because that's how you reflect over that line. And notice again, we get the same answer, right? So our parameterization that we get here is exactly the same as the parameterization that we got here, just by way of 2 different arguments. Now, for this particular example, take your pick. It doesn't matter. You get the same answer. Suit yourself. For all other examples, right, as you try to figure out how you're going to solve problems, remember, every situation is different. Every situation calls for a different tool. So don't throw away your tools. Right? You're going to need, there are some situations where this point of view right here is essential and this won't work. And there are some situations where this point of view right here is essential and this won't work, right? So the point to this is not the answer. The point is the methods. Is everybody on board with that? All right. Okay, now this was, fun and games with parameterizations, cool and all that, but do notice the answer we got, negative pi, is indeed the negative of the answer we got going the other way, which was positive pi. So as it should be. So how about this? How about we just save ourselves huge amounts of trouble? We don't have to parameterize anything. We can just say, this curve that you've asked me to parameterize, that's the same as the curve that I already know how to parameterize, just oriented backwards. It's literally the opposite orientation on a curve I already know. And when you have a backwards orientation that will insert a minus sign on the answer, namely just take the negative of the integral that we already computed. The integral we already computed, we already know is pi. So that's why the answer here is minus pi. That's way easier in this case. Everybody happy with that? All right, so that's method number 3. Let me talk about method number 4. Method number 4 I don't endorse. Method number 4 will get you the right answer. Let me remind you, that's not what we do here. We're not interested in answers, we're interested in reasoning. Right? Method number 4 says, I already did a bunch of work here, and if I want to go the opposite way, then can't I just take this integral and acknowledge the opposite direction by rewriting this as an integral from pi to 0, and then, everything else the same? I'll totally get you the right answer. Numerically, at the bottom of the page, put a box around it. Remember that thing we don't care about, right? That it will be correct in that way that we don't care. Let's think about the reasoning, though. This seems to be making a reference to what I'm going to call time travel. In the sense that, the way we set up this parameterization in the first place was t. Let's be honest, we tend to think of t as being time, and time, in our experience anyway, goes forward, right? So from the lower value to the higher value, this kind of looks like you're suggesting time be moving backwards. And I have questions, right? How does that work, right? Is this a sci-fi movie, right? Or is this, what's that director that does all the wacky sci-fi movies? Anyway, sure. So now again, it's not that it gives you the wrong answer. It's that it unnecessarily brings up a lot of really concerning big questions that would have to be addressed in order to actually draw any conclusions about what this actually is and whether this makes any sense. And so it pokes a lot of holes in your reasoning. So I say, why would you want to subject yourself to an argument that is vulnerable to complaints, when in fact all you need is a minus sign, and that minus sign is much more naturally addressed, no questions, like we did here. So I please don't do this whole time travel, time moves backwards thing. I think that's a bad argument. Okay. Everybody good? All right. Now here's a new question. We've talked about how to interpret line integrals, vector line integrals, when f is a force. Specifically, when f is a force, the integral represents work. In fact, that was our motivating example. So this is actually the only example we've seen yet of a vector line integral. Is right now we know one thing it can do. It can compute work when f represents a force. I'll remind you, though, we have another very common interpretation of vector fields. What if f represents the velocity of the flow of a fluid? That's not a force. Not a force at all. If that's what f is, right, then, okay, well, then now what does that represent? It's not going to be work. The vector field's not representing force anymore. So what is it? Right, a very reasonable question. It's turns out to be kind of a weird question. One of the unfortunate things about this question is that the answer is not something that you have a pre-existing familiarity with. We kind of got lucky with this first scenario. Well, forces, y'all already kind of understand. Work, energy, right? Something you kind of already understand. Nice, crisp, succinct answer is something we're already aware of. I'm sorry to report that's not going to be the case here, right? This thing, what the vector line integral represents when you're talking about fluid flows is not going to be a pre-existing familiar object. And that's a little disappointing, but you just have to kind of prepare yourself. Okay, well, it's going to be some new thing, and the question shouldn't be what specifically is it. The question should be, how should I understand this? How should I understand vector line integrals in this context? And I'm going to get that by, I'm going to answer my question with a question. That'll work out. This is just a recall for convenience, convenience of reference, because these are useful objects as we compute. Nothing new there. And here's the question I'm going to ask. We've got a curve. We've got a fluid flowing around in some way. And I'm going to imagine this thin region, kind of a tube of sorts, but it doesn't have walls. This is not actually a tube, but this thin region that I have colored green there. And I just want to talk about the fluid. You might say, I want to talk about the fluid that's near the curve. Not necessarily on the curve, just near the curve, as described by, I want to keep track of these cross-sectional areas here, whatever that cross-section is. And the question I'm going to ask about this fluid is, looking at all of that fluid, to what extent is that fluid flowing along the curve? And it kind of seems to come out of nowhere, but nearby fluid is flowing. To some extent, it's flowing along the curve. To some extent, it might be flowing perpendicular to the curve. Let's kind of forget about that whole perpendicular thing. Let's try to keep track of to what extent is all of this fluid as a whole flowing along the curve. And good news, this question is actually pretty easy to answer, because I can chop this fluid up into little pieces of fluid. And that amount of fluid is just area times thickness. And I can keep track of how it's flowing along the curve, because keep in mind there is a vector field given that tells me the actual velocity, and I want to know this part, the extent to which it's along the curve. That's just a component, no big. Right? And so altogether then, if you're interested in looking at all the fluid, and for each piece asking how much does that flow along the curve, and then you want to add up total altogether for all of the fluid, how much does it flow along the curve, you get this expression right here, which simplifies like that. Details, make sure you check the details, of course. Yeah. Okay, so we kind of have an answer to the question, but we also have something about this that is a little uncomfortable, and I want to point that out before we celebrate. It depends on the area. The area is this arbitrary thing that I introduced. Why did we introduce an arbitrary area there? What purpose does that serve? I needed to be able to talk about fluid, and fluid has volume, and I can't get my hands on that if I'm looking on a one-dimensional curve. I needed to kind of fatten that up so I could talk about actual fluid, right? But I'm not actually interested in the area. I'm actually interested in the curve itself. So the fact that my answer depends on area is a necessary relic of the way I got my foot in the door. It's not really what I want. What I want to know is per section area, right? I mean, obviously more area means more fluid, means more of what the question's asked. So let's kind of factor that out by getting rid of it, by just kind of dividing by it. Per section area, the answer to our question up here, per unit area, is the line integral. So this is actually, I think, a really nice way to think about what vector line integrals represent in the context of fluid flows. Vector line integral, if f represents velocity, the vector line integral, it basically answers this question: how much is the fluid flowing along the curve? It's just, okay, yeah, but in order to make any sense out of it, we have to talk about cross-sectional areas that we don't care about, and then we throw away at the end. So that's the big idea. And again, this is not something you're previously familiar with, probably, but that is how you think about these things. And we're out of time, so we'll draw the line right here. See y'all later. Have a good rest of your Monday. Don't forget about attendance.